enters them from a certain angle and gets bent, and it turns out that the rays bunch up at an angle of 22 degrees away from the sun. So in the case of the rainbow, it was 40 or 42 degrees in the direction opposite to the sun. In the case of the halo, it's a 22-degree angle, but in the direction of the sun. That's where the rays bunch up. So the diagram could look something like this. You're looking roughly toward the sun, but you want to look a little bit away from it, and at an angle of 22 degrees. And all around the sun, then, there's this concentration of light because the rays have bunched up, and it forms this circular halo around the sun. Now, the ice crystals are up there because they're thin cirrus clouds, and the cirrus clouds can exist high in the atmosphere even when it's quite hot at ground level. Here's a halo that was taken when surface temperatures were about 80 degrees on the ground, but way up in the atmosphere, temperatures are below freezing, and these thin pencil-shaped hexagonal ice crystals can form and produce the halo of light. You can see that red is on the inside and blue is on the outside there. Again, it's best to block the sun so that it doesn't appear so bright. And if you position a person judiciously, you can see sort of a saintly figure. Not only is there the halo caused by the ice crystals, but there's the diffuse glow of the sun itself bending around the person's head. So it kind of looks like a saint here. But anyway, you don't have to block the sun, especially if you are using digital cameras, because they have, at this time, sufficient dynamic range to be able to record bright things and faint things. And here, in fact, is a photograph of the halo taken with a digital camera without the sun being blocked. And, you know, the sun is very overexposed here, but that's okay. You can see the halo quite nicely. And with old photographic emulsions, you couldn't do this. They wouldn't have such a dynamic range. The sun would be so overexposed that it would bleed into the halo. But with modern digital cameras, it's actually quite easy to record these phenomena. If you can see it, you can photograph it. Just point a camera up and shoot. All right, well, related to the solar halos is a phenomenon known as sundogs, or mock suns. They are a particularly bright part of the halo. So here's the halo being blocked by a lamp, and you can see it goes all the way around the sun, but there's a concentration of light to the left of the sun and to the right of the sun at nearly the same altitude above the horizon as the sun is. They're a little bit higher. You can see these concentrations. They're a little bit farther out in radius than the main part of the halo. You can see the inner edge of the halo is there, the outer edge is right about there. So these things are near the outer edge of the halo, and they are a particularly bright concentration of light in this halo. So people call them mock suns, or sun dogs, kind of like a dog following a person around. And indeed, here's some Arctic sun dogs. You can see the sun dogs just above the horizon here, and you can see the Arctic dogs pulling this sled here. So that's kind of an interesting juxtaposition. These guys are produced, again, by hexagonal ice crystals, but in this case, instead of being long and skinny and shaped like a pencil, these hexagonal crystals are flat and plate-like. And by tracing the rays and how they enter the ice and how they exit, by doing the so-called geometrical optics, you can figure out that indeed the sundogs are at a location where there would be a particularly big concentration or bunching up of these rays coming through the hexagonal ice crystals. These sundogs can be so bright that you can often see them without seeing any part of the rest of the halo. So here's a good example. There's the sun conveniently behind a cloud, so it's not too overexposed. And here, 22 degrees away, is a sundog with red on the inside and blue kind of indistinct on the outside. It's amazing how often you can see these things. Just look up into the sky when there are clouds passing overhead. Cirrus clouds in particular, high, thin, wispy clouds, not thick thunderhead type clouds. Here's a solar mock sun, or a sundog, with the sun actually to the left off the screen here, and there's Mount St. Helens, a volcano that erupted in the early 1980s. Well, there's a bunch of related phenomena to the sundogs and the solar halos. If you have very clear conditions and very cold conditions, where your view of the sun and surrounding areas is pretty unobstructed, yet there are ice crystals up there, that are able to bend or refract the brilliant sunlight, then you can sometimes see some very, very faint phenomena. Here's a good example. There's the sun, partially blocked by these trees. There's the primary halo, 22 degrees in radius, and some sundogs. But you notice here there's a secondary halo, way out here, at a radius of 46 degrees, halfway up from the horizon to the point overhead, the zenith. And you can see some other things here. These are known as tangential arcs, and there's a bunch of them. There's one right there. There's one. There's also a big circular arc that joins the sundogs with the outer halo and then keeps on extending outwards. Just a brilliant range of phenomena that can be seen where you have very clear skies, aside from some ice crystals in thin cirrus clouds high in the atmosphere, but otherwise very clear skies and nice and cold conditions so that a bunch of these crystals can form. I personally have never seen the outer halo because I've never been in a cold enough place at the right time to see them. Here's another example of the variety of arcs that can form from different kinds of hexagonal ice crystals bending light through different angles and causing a bunching up of the rays. Again, similar to what I described in more detail for the rainbow, but different in particular circumstance for each of these different phenomena. But they're beautiful to look for. Now you can also see a halo around the moon. It's fainter than the solar halo because the moonlight is fainter than the sunlight, but it's often more obvious than the solar halo because it's easy to look up at the full moon. People often do. It's kind of romantic. And if there are clouds in the sky, you will often see a 22-degree moon halo. People tend not to look up at the sun in the sky because it's just so blazingly bright, so people don't want to look up at the sky. If you look up during the daytime, you will often see halos, but they're easier to notice around the moon because the moon is not so blindingly bright. And here's another example of a lunar halo and the International Space Station streaking across the sky next to it. Another related phenomenon is called the corona. Now, the corona is in the direction of the sun, and blocking the sun here makes it easier to see, but you can see these multicolored halo-like rings around the sun, but they're much smaller in angular extent than the solar halo that we just discussed. The solar halo that I first discussed was 22 degrees in radius. It was big, like that. This is small. It's right in the direction of the sun, and they're just these little rings of light, okay? They're called the corona. They have nothing to do with the outer atmosphere of the sun. The outer atmosphere of the sun is also called the corona, and you can see it beautifully during total solar eclipses. And it's unfortunate that the atmospheric corona bears the same name. But, that's the way it goes. You just have to live with it. The corona is caused by the fact that light is not only bent when it goes through a droplet, it's also bent when it goes past a droplet, it turns out. That's a phenomenon known as diffraction, and I'm not going to discuss it here because it gets quite complicated. But the point is that the light gets bent, the different waves get bent by different amounts, and the path lengths are different, and they can then interfere with one another. You can get constructive and destructive interference, much like that which caused the supernumerary bows, okay? So you get these coronas around the sun and also around the moon. And you can also see them if you look at a bright headlight through fog. I'm sure many of you have seen these things looking at distant cars through fog. You will see this corona around the headlights, and it's caused by this bending of light around droplets and the constructive and destructive interference of that light with itself. Related to the corona is a phenomenon known as the glory, which is seen on the opposite side of the sun. And it's very difficult to see, but here I captured it when I was on top of Mount Hamilton, the location of Lick Observatory in California. Here's the shadow of the mountain. Here's actually the shadow of one of the domes. And around this, there's this very thin, almost imperceptible corona. You can see it nicely around the shadows of airplanes sometimes. Here's a beautiful example of it, where there's the shadow of the airplane on the cloud deck down below. The observer is sitting near the front of the plane. I can tell because the center of the glory is the perspective of the person viewing it. So the person must be right there, not at the tail end. And so that's the glory. And it's again caused by light bending around and within water droplets. But in this case, the incoming sunlight comes in something like that. It gets bent or refracted. It also gets reflected, and then it comes out again. And this simple picture doesn't quite work because the angles don't quite work out. It turns out you also need what's called surface waves traveling through the raindrop a little bit. And people still aren't completely in agreement as to how the glory forms, but it's something like what I've illustrated in this simple diagram. Now, yet another phenomenon that you can see in the daytime sky relating to ice crystals is what's called the sun pillar. All right? So if you look at the sun, here in this photograph you happen to see a sundog in the very same frame, but here's the sun. Below the sun there's a column or a pillar of light. This is not an artifact of the photographic process in this case. This is an actual column of light produced by light reflecting off of ice crystals. And the ice crystals are the flat hexagonal variety that we encountered before. They're these plate-shaped things that produce the sundogs, the mock suns. So the phenomenon is quite similar to what happens when sunlight reflects off of the ripply water of a pond or a lake. When the water ripples like this, the angle of reflection varies with time, and sometimes, at some moments, any small part of the water might direct the sunlight or the moonlight toward you. And the angle is different for this light here near the bottom of the pond than it is for that light there if the pond is very close by. So you get this phenomenon then with these plate-like crystals hanging around in the atmosphere. They're parts of these cirrus clouds. And in this particular photograph, the sun has actually already set. But there's a bunch of plates above the sun in the atmosphere, and they are reflecting the light, much like the light was reflected in the previous photograph that I showed you off of the pond, and you are seeing that as a pillar in the sky. Here's a particularly bright pillar that you can see after the sun has set. Indeed, the pillars are easiest to see after sunset compared with before sunset, because before sunset you've got to contend with this bright sun shining in your eyes, and the faint pillar is relatively hard to see. But after the sun has set, you don't have the competing effects of the sun in your way. Now, sometimes you might think that there shouldn't be a pillar because you don't see any obvious clouds, yet in fact the pillar is there. And here's an example. The clouds are mostly above the horizon, way up here, but there are some thin ones there that produce the pillar. And indeed, when you have nearly transparent, thin clouds of this sort, you get an enhanced effect because you're not dealing with light reflected every which way from clouds. I mean, here, if the pillar were on top of these clouds there, it would be much less distinct. The contrast wouldn't be as great because you'd have to contend with all the competing light coming from all the other directions. So here's a beautiful, beautiful example of a pillar. Well, I hope in this lecture I have shown you that you don't have to be bored while waiting for nightfall. There are plenty of beautiful things to see in the daytime sky, full of color, full of wonderful geometry, all produced by the complex interaction of light waves with water in its liquid state and in solid form with ice crystals.